This is geometry lesson 8.4, the areas of triangles. And the big idea says from the rectangle area formula, the area formulas for both right triangles and any triangle can be deduced. All right, so we know that the area of a rectangle is base times height. And this illustration here shows you that if we take that same rectangle and we cut it in half across its diagonal, we create two triangles. And so therefore this shows you why the area of a triangle formula is area equals 1/2 base times height, because just the base times height is your area of a rectangle, and by creating a triangle, we're taking half of that area. Each one of these triangles would be congruent to each other, and therefore their areas would be the same. So we're going to look at this formula for right triangles and also just for any old triangle. But for a right triangle, it's very basic and very simple. So it's 1/2 base times height. You'll notice that this particular textbook puts the height in front. They have their own preferences for that. It doesn't matter how you write it. If you write base times height, that's perfectly fine. If you put the height up front, that's fine too. We're multiplying these three things together, 1/2 times height times base, and the order that you multiply numbers together does not matter. So it doesn't matter how you place that. So the base and the height of a right triangle, which is what we're going to start with here, are the two legs of that right triangle. If you remember back to the terms that we use when describing right triangles, coming out from the 90 are the legs, and then that other diagonal side that's across from the 90 is your hypotenuse. So when we go to find the area of a right triangle, we don't worry about the hypotenuse at all. We're just looking at the two legs. It does not matter which one you call the height and the base. When it's sitting like this, we tend to take the bottom one and use it as the base, and then the vertical one and use it as the height. But it does not matter, again, because we are multiplying those two numbers together. Order doesn't matter. So just look for your 90-degree angle, and that's going to show you where your base and your height are. Those are your two legs. All right, so real quick example. We're going to find the area of triangle DOG here at the right. And so we've got three numbers. We just need to make sure that we ignore the hypotenuse, which is 15, and just look at the two sides that are creating the 90-degree angle. When we get down to regular triangles that are not right triangles, we're still going to be looking for that 90 degrees to tell us what's the height or the altitude, and then what's the base. All right, but for this straightforward right triangle problem here, it's 1/2. I'm going to write base times height because that's just what I'm used to. So it's 1/2 times, doesn't matter which one you call the base. I'm just going to put 9 there, and 12. Again, I'm not using 15. And so you can do these in your head too. You can multiply in any order. So we don't necessarily want to take 1/2 of 9 in our head, which is 4.5, and times by 12 makes things difficult. You can go in any order. Half of 12 is 6, and 6 times 9 is 24. I'm sorry, 54. Okay. Now you could do this in your calculator as well. Just do 12 times 9 times 0.5, and you'll also get that. But obviously speed is nice sometimes, and so taking half of 12 is super easy. It's 6, and we all know 6 times 9 is 54. So it gets us there real quick. But we can also use the calculator. You could use the fraction function, or 0.5 is fine. All right, so for a regular triangle now, we're still using the same exact formula. We're just looking for those things in different places. So you'll notice in the picture, we've got the base across the bottom, which is not always going to be the case. And then we've got the height dropped here, and this is the key. It's hitting at 90 degrees. Okay, so the height or the altitude is always going to come from a vertex, so one of the corners. Across the triangle, sometimes it'll be outside the triangle. We'll look at that down here. And it has to hit the base or an extension of the base at 90 degrees. If we don't see an angle of 90 degrees, we cannot be sure that we actually have the altitude. So every triangle actually has three different heights that pertain to three different bases. Okay, I could go from this vertex to this side, 90 degrees, and clearly that height is bigger than this height. But the measurement of this height times this base, and then take half, will get me the same answer as this height times this base. And then the same thing for this one. Now 90 degrees from here would actually be out here somewhere. And When we extend a side, like we'll look at down here, we don't use that extension as part of the measurement of the base. We use the actual base, and then this would be your height out here. So every single triangle has 3 possible heights and 3 possible bases, but as long as you're using the two that are hitting at 90 degrees, you're going to get the same answer for the area. That's what's nice about these. So then, again, real quick, you've got your traditional looking height and base here, where the height is measured inside the triangle. It hits the other side at 90 degrees. So the length of CD would be the height or the altitude, and then the length of AB, that would be your base. You would just multiply, multiply, take half. So when we have an obtuse triangle, see this angle in here is obtuse, more than 90. We still have to measure from a vertex to the side or the side extended at 90 degrees. That's opposite that vertex. So we would measure BA as the base and then CD as the height. We don't count this extra little line down here, DA, as part of the base. It's not part of the base. The triangle's right here. So it would be the length of BA times the length of CD for base times height. So sometimes we do have to extend a side to get it. Now remember, there's 3 heights for every triangle. So this one also has a height that comes down like this, 90 degrees, and that one would get multiplied by this base. So you just look for the 90 and the 2 lines that are hitting at 90 degrees. Those are going to be your base and your height. Okay, so that would be the height times CB. Take half will give you the same answer as this height times this base. All right, now we just need to be careful again, like I said, when the measurement of the height is used outside of the triangle, we are still just using the actual side length of the triangle as the base. And then, of course, with a right triangle, the 2 sides are actually the base and the height because they're hitting at 90. So the key is look for your 90. Your base and your height have to be hitting at 90 degrees. All right, let's try a couple practice problems on the back. So example number 2, we've got this one picture that's got a whole bunch of different triangles in it. You've got the large triangle ABE. You've got this little triangle ABC, ACD, ADE, and then you've even got those overlapping triangles that we looked at with proofs like ADB. So each one of those, if you look at this picture, all those triangles that I just named all have the same height. If I go from A down to what is the x-axis, which part of that x-axis is the base of all of those triangles, they all have the same height. And so all we're doing, so if you look at ABC, the base is from B to C and the height is from C to A. And then if we even go to the big triangle here, AEB, the base goes from B to E, but the height still goes from A to C 90 degrees. We don't measure the height diagonally. It's not one of the sides necessarily unless you have a right triangle. Okay, so we measure from the top vertex down to the base. So for all of these triangles that we're looking at here, we're actually going to use the same height, which is 6 in this case. We're going from 0 on the x-axis all the way up to 6. Okay, so here we go. Area equals 1/2 base times height. We are starting with ABD. If you like to highlight, you can highlight it, ABD. And so again, the height here is 6. So I'm going to put that in first for all of these so we see the consistency. Remember, it doesn't matter which one you call the base and the height here. So I'm going to call that 6. So really, if I was going to write it like that, I would probably want to write H times B, but that's really not important. And then you would count across the entire base here. So from here to here is 7. And then we have 1, 2, 3. So this should be a total of 10. Oh, I'm sorry. ABD, I went all the way to E. So height is still 6, but looking at ABD, sorry for the confusion, we're looking at the base that goes from B to D. Okay, so that's not going to be 10. We've got 3, 4, 5, 6, 7. Apologize for that. So the height is 6. The base from B to D is 7. Half of 6 is 3 times 7 is 21. And we don't have any units here, so I'm just going to leave it as 21. Remember, it's always your units squared, though, if we do have them. Now, ACD still has that same height of 6. This looks like a right triangle. We know that a vertical line on a graph and a horizontal line are going to hit at 90 degrees. So now the two sides are the base and the height. So area equals 1/2 base times height, or height times base, however you want to write it. I'm going to leave the 6 there in front from A to C. We're using this little skinny triangle here. The height is still 6. And now the base between C and D is 2. Half of 6 is 3. 3 times 2 is 6. Okay, ADE, this little one over here. The height is still measured from the top, straight down 90 degrees to the base, or the extension of the base at 90 degrees. So we're still using this as the height. Now, if you were given a diagonal here, not necessarily, I wouldn't use the word diagonal there actually, but if you were given the height here, then you would have to use this side as the base, but that's not what we're given here. We know this measurement is from this vertex 90 degrees down. It's the extension of this base. So AC is still the height. Okay, so it's still going to be 6. I'll write this one HB. Again, doesn't really change anything. So the height is 6, and then be careful, the base is just 1, 2, 3. This down here, we don't count the extension of that side as part of the base. That's just used to help you measure the 90 degrees straight down. So 1, 2, 3. Half of 6 is 3 times 3. Area of that triangle is 9. And then triangle ABE, the really big triangle. This was the one that I started out trying to solve on accident. The height of that is still 6. And now the base is that 10 that I was looking at. So all the way from B to E for this bigger triangle, it's 10. Half of 6 is 3 times 10 is 30. All right, we're basically going to go through the same exercise here for the additional example. So what I would ask you to do is to quickly pause your video and then try these, and then replay your video and see how you did on those. Trying them first will probably get you the biggest benefit. Okay, so hopefully you paused the video and you already tried these. So let's take a look and see how you did. Letter A, P to Q to S. This looks very similar to the first one that we had. It's just kind of turned on its side. So when I see P to Q to S, this triangle here, I'm looking at this as the height and this as the base. Remember, when we have these diagonals here, we can't just measure boxes across and call that 6. If you actually laid that down, it's longer than 6. So we couldn't use QS as the height and then this as the base. They don't hit at 90 degrees, first of all. But we can't measure that without using our distance formula or something like that. So the base and the height need to hit at 90 degrees. So we're going to use PR as our height and then QS as our base. So area is 1/2. I'm going to go height times base here. And so the height goes from 0 to 6. So our height, again, just like in the problem above, is 6 of that triangle. And then the base goes from 0 to 5. You can always just count boxes. 1, 2, 3, 4, 5. So the height is 5. Half of 6 is 3 times 5 is 15. Okay, letter B, PRS, the little skinny one. PR is still the height, 90 degrees hits right here. So we're still going to say height times base. The height is still 6 of that triangle, and now the base there is just 2. Half of 6 is 3 times 2 is 6. Letter C. PST, we're using this slanted triangle here. We still measure the height out here, and that's why these problems are important, and that's why I put them on here, so that you can see the height can be measured outside of the triangle. This would be the base, this would be the height. This base and the extension of it hits the height at 90 degrees. So the base is just 1, 2, 3, and the height is still 6. So it's 1/2. We'll use 6 as the height. 3 from S to T is the base. Half of 6 is 3. 3 times 3 is 9. And then the last one, PQT, the real big triangle, still using this as the height. So 1/2 height times base. We're going to use 6 as the height. And now the base goes all the way from Q to T. So 1, 2, 3, 4, 5, 6, 7, 8. So 1/2 of 6 is 3 times 8 is 24. All right, so very repetitive. You just need to make sure that you are pulling the two sides in a right triangle or the height that hits a base at 90 degrees, even if it's outside the triangle for your base and your height. All right, example number 3. One quick problem on kind of working backwards when they give you the area and one of the sides and you have to work backwards and find it. Talk about 2 quick different ways that you can do it. So first of all, we're still using this formula 1/2 height times base or base times height. Either one is fine. They tell you that the area of this triangle is 48. So 48 is going in right there. That's the area. And if the height is 8, so the height is 8, we're going to find B. So you could sit there and kind of think about it in your head. A lot of you are really good at reasoning through that. But let's do it algebraically by plugging into the formula and showing our work. So 48 goes in for area. That's what it is. 8 goes in for the height. And then we don't have the base. So I think the easiest way to do these is to get rid of this fraction. We don't like dealing with fractions in equations. So because the 8 is sitting next to it and part of this equation is to multiply those together, we can just go ahead and multiply 1/2 times 8 right now and just simplify this equation. And then it's super easy at that point. So we're not doing anything with the 48. 1/2 of 8 is 4. And so I still have 4 times b. And now it's a straightforward equation. You're just going to divide by 4 and b equals 12. And you can always double check yourself. If this was 12, that's what we're calling it, and h was 8, you would do 12 times 8 and then take 1/2 and make sure that you get 48. And you do. Now let's talk about one other way to do this algebraically, just for the sake of seeing it and remembering how to handle fractions. So still plugging everything in the same here. One way to clear out a fraction algebraically, like let's just say the 8 wasn't here and it was 1/2 b. How do I get rid of that? Well, especially when there's a 1 on top, you just end up multiplying by what's on the bottom. So this whole side gets multiplied by 2. This whole side gets multiplied by 2. Now, when you do that, you don't multiply everything here by 2 because these are not separate terms. There's no addition here. We know that if we distribute a 2 and there's a plus or a minus sign, everything gets it. But all of this is just one term. So I only multiply the 2 times this one term. This is an entire term right here. So first of all, 2 times the 48 is going to be 96. And what ends up happening is 1/2 times 2 is just 1, which we don't have to write that multiplication here. Technically, we could put a times 1 because 1/2 of 2 is 1. But that's the whole point of multiplying by this, because basically if I'm creating a times 1, I'm clearing it out because it doesn't need to be written. So just a reminder of how you clear out a fraction like that. You just multiply by the denominator and it clears it. If there was a different number on top, it would still remain. So we did this 2 canceling this 2 and we were left over with a 1, which we don't write. But let's say this was 3/2 and you multiplied. The 2's would clear and you would still have a 3 times 8 times b. Now, I don't think you're going to really see that very often, but just reviewing some basic algebra skills that we do need every once in a while. All right, at this point, you would go ahead and divide, and then sure enough, you would end up with the same answer. So of course, this is the way I would tell you to solve it, but just going back and reviewing some basic algebra in case we need it.